Hello, I'm Divyashree Mary, working as Assistant Professor in the Department of ECE, SJBIT. In today's lecture, I'll be explaining about the detection of PPM wave. In the last class, in the last video, I have explained about the generation of PPM. So in today's video, I'll be explaining about the detection. So here, consider you have a PPM wave S of t, which is having been done with the uniform sampling, and we'll assume that the message signal M of t it is strictly band limited. So the operation of one type of PPM receiver is as follows. The first method, that is, convert the received PPM into PDM wave with the same modulation technique. This is the first step, converting the received PPM wave back to the PDM wave. Second method is integrate it. Integrate this PDM wave using a device with a finite integration time, thereby computing the area under each pulse of the PDM wave. So this is the second step. Third one is sample the output. Sample the output of the integrator at a uniform rate to produce a PM wave whose amplitude are proportional to the signal samples MNS of t of the original PPM wave S of t. Last step is the demodulate. Finally, we will demodulate the PAM. Demodulate the PAM wave to recover the original message signal S of t, M of t. So all the operations described here, all these four operations, they are linear. In addition, a practical PPM receiver, it includes a non-linear device called a slicer. So, the slicer will be at its input end. The input output characteristics of an ideal slicer, it is shown as in the diagram figure, where the slicing level is normally set at approximately half the peak pulse amplitude of the received PPM wave. The function of the slicer is to preserve the positions of the edges of the received pulses and to remove everything else. What is the function? It is to preserve the position of the edges of the received pulses. So it does so by producing almost the rectangular pulses with fairly sharp leading and trailing edges at the same instant as the corresponding edges of the received pulses. So this is the message signal, this is the slicing level. So at this point, at approximately half, there will be a slicer output, which is a pulse, and that is delayed. So the slicer acts as actually a noise cleaning device. In that the final noise at the output of the receiver, it is greatly reduced by eliminating all the noise in the received PPM wave except in the neighborhood of say trailing and leading edge. So the output of this slicer, it is differentiated and then half wave rectified, which yields a very short pulse each time the amplitude of a pulse in the received PPM wave passes through the slicing level. So this diagram, it shows the nth pulse of the PPM. Here it is a short pulse which is produced as the pulse passes through the slicing level, and here it is an appropriate delay when it is applied to this short pulse, and then this is the corresponding PD. Yeah. So having converted the received PPM signal into the PDM wave with the same modulation, the receiver then proceeds to reconstruct the original baseband signal M of t. So this is how we'll detect a noiseless PPM wave. So how is the noise having an impact in PPM? So in a PPM, the transmitted information, it is contained in the relative positions of the modulated pulses. The presence of additive noise, it affects the performance of such a system by falsifying the time at which the modulated pulses are judged to occur. Immunity to noise will be established by making the pulse build up so rapidly that the time interval during which noise can exert any perturbation is very short. Indeed, additive noise would have no effect on the pulse positions if the received pulses were perfectly rectangular, because the presence of noise introduces only the vertical perturbations. The reception of rectangular pulses implies an infinite channel bandwidth, which is of course impractical. Thus, with the finite channel bandwidth, we find that the received pulses have a finite rise time, and the performance of the PPM receiver, it is affected by the noise. As with the continuous wave modulation system, the noise performance of a PPM system may be described in terms of output signal to noise ratio. Also, to find the noise improvement produced by the PPM over a baseband transmission of a message signal, we may use figure of merit, which is defined as output signal to noise ratio of the PPM system divided by the channel signal to noise ratio. Thus, we can say what is the performance. So, let me discuss about the figure of merit signal to noise ratios of PPM. SNRO is given by the equation pi square Vt Ts square A square divided by 32 N naught. So this is the output signal to noise ratio assuming a full load sinusoidal modulation is done, and then the signal to noise ratio with respect to the channel, it is 3 A square divided by 4 Ts Bt W N naught. So the figure of merit is having the ratio of these two. It is pi square by 24 into bt square ts cube into w. So in the noise analysis for PPM, we assume that the average power of the additive noise at the front end of the receiver is small compared with the peak pulse power. So it is assumed that there are two crossings of the slicing levels for each pulse, that is one for the leading edge and one for the trailing edge. A Gaussian noise will have occasional peaks that produce additional crossings of the slicing levels. However, the analysis neglects the false pulses produced by high noise peaks. It is apparent that these false pulses have a finite, though very small, probability of occurrence when the noise is a Gaussian one. No matter how small it is, standard deviation it is compared with the peak amplitude of the pulses. As transmission bandwidth is increased indefinitely, the accompanying increase in average noise power eventually it causes the false pulses to occur often, thereby causing the loss of wanted message signal at the receiver output. We thus find that PPM system suffers from the threshold effect. Next we will see bandwidth and noise trade-off. In context of noise performance, a PPM system, it represents the optimum form of analog pulse modulation. The noise analysis of a PPM system presented in the preceding example here, it reveals that the PPM and frequency modulation system exhibit a similar noise performance. Means you need to know 2 points. One is both systems have a figure of merit which is proportional to the square of the transmission bandwidth, BT square, and normalized with respect to the message bandwidth. And the second point what we have observed is both systems exhibits a threshold effect. Threshold effect as the signal to noise ratio is reduced. So the practical implication of point 1, it is that in terms of trade-off of increased transmission bandwidth for improved noise performance, the best what we can do with the continuous wave modulation and analog pulse modulation is to follow a square law. Square law. So what is the question what comes to our mind is, can we produce a trade-off better than the square law? Yes, we can do it, and digital pulse modulation is the way to do it. So instead of going for analog pulse modulation, you can go for digital pulse modulation. The use of such a method is a radical departure from the continuous wave modulation. There are two fundamental processes involved in the generation of a digital pulse representation of an analog signal. One is the sampling and another one is quantizing. Quantization. The sampling process takes care of the discrete time representation of the message signal for its proper application. but we have to follow the sampling theorem as well. The quantization process take care of the discrete amplitude representation of the message signal. Quantization is a new process. I'll explain it in the upcoming videos. So for now, for time being, we can say that the combined use of sampling and quantization, it permits the transmission of a message signal in a coded form. So it makes us to realize an exponential law for the bandwidth noise trade-off. For analog modulation, square law. Here, exponential law. So let us take an example for PPM. PPM, when it is used in a impulse radio. Traditional digital transmission systems attempt to minimize the bandwidth of the transmitted signal. Filtering is often applied to rectangular pulses to reduce the occupied bandwidth, but a method does not follow this philosophy and has captured attention recently. It is the impulse radio. With this technique, information is sent by means of a very narrow pulse that are widely separated in time. Since the pulses width are very narrow, the spectrum of the resulting signal is very broad. And also you can say that this technique is a form of ultra wideband radio transmission or impulse radio. One type of pulse used for impulse radio is Gaussian monocycle, which is based on the first derivative of the Gaussian pulse. The waveform of the Gaussian monocycle, it is given by the equation V of t is equal to T by tau into exponential of minus 6 pi to t divided by tau to the square. So this is what is the equation, where A is the amplitude scaling factor and tau is the time constant of the pulse. This signal, it is normalized to unit amplitude. It consists of a negative lobe followed by a positive lobe, something like this. Negative lobe and then a positive lobe. With a total pulse width of approximately tau. For impulse radio application, the pulse width tau, it will be between 0.20 to 1.5 nanosecond. The spectrum of a sequence of these pulses can be obtained from the Fourier transform of an individual pulse, and the frequency axis will be normalized in terms of time constant tau, where tau is equal to 1 nanosecond, and the frequency axis ranges from 0 to 5 gigahertz. So this is amplitude, and the y-axis is the normalized time t by tau. So there are several methods for digitally modulating such an impulse wave. One method is the PPM. With this method, there is a nominal time separation Tp between the successive pulses. To transmit a binary 0, the pulse transmitted is slightly early minus Tc. To transmit a binary symbol 1, the pulse is transmitted is slightly late plus Tc. So the receiver detects this early or late timing and it demodulates the data accordingly. So the separation between the pulses TP, which ranges from 1000 nanoseconds to as little as 25 nanoseconds, it results in data rates ranging from 1 to 40 megabits per second. So uh, the ultra wideband nature of the modulated signal, it has both good aspects and bad aspects both. Since the signal power is spread over a large bandwidth, the amount of power that fails in any particular narrowband channel, it is small. But the power falls in all such narrowband channels consecutively. There is a concern that ultra-wideband radios will be more harmful interference into the existing narrowband radio frequency service, which occupies the same radio spectrum. So as a result, although ultra-wideband radio has been allowed in various jurisdictions, there is a strict limitations on the power that may be transmitted. Due to these limitation of the power, ultra-wideband radio is limited to only a very short range applications, say for example less than few hundred meters. So this is one of the applications where you can see PPM in practical usage. So in the next video, I'll be explaining about the quantization process. Thank you.